Let's apply the fundamental theorem to do some fairly straightforward definite integrals. The first integral is a computation from 4 to 8 of the function x over the square root of x squared minus 15. Well, this is just a basic substitution as we learned from our antiderivatives. So first what we're going to do is we're going to write the square root with the negative 1/2 power. And then of course note by the chain rule that the derivative here is 2x. Now we have an x here, but we don't have the 2, so we're going to put in the 2x and then adjust for it using our properties of the definite integral. And now of course we're ready. We've got u to a power du, so add 1 divided by the new power. So now we have our 1/2, we have our new power of 1/2, division by 1/2 is multiplication by 2, and so now we have an antiderivative. Notice here we don't have to say plus c because it's just going to subtract away when we apply the fundamental theorem. So no need to dress this up with an arbitrary constant. And so now of course the 1/2 and the 2 absorb, and now we want to use the fundamental theorem. So basically we have our antiderivative evaluated at 8, so that's going to give us a 64 minus 15 square root, and then the lower limit will give us a 16 minus 15 square root, of course with the negative, so the f of b minus the f of a. Then of course the 64 minus 15 gives us 49, and of course the 16 minus 15 gives us 1, so we have 7 minus 1, which is 6. Now the next two integrals are just very straightforward trigonometric integrals, not difficult, but very fundamental. So again, what we want to do here is integrate sine x from pi over 2 to 3 pi over 4. Now of course, the antiderivative or an antiderivative of sine x is just the negative cosine x. And so that's very simple. We just work the differentiation formulas backwards. And so now we can factor the negative that we have here and then just evaluate at 3 pi over 4 and pi over 2. Of course, cosine of 3 pi over 4 is just negative 1 over root 2. We just think of the reference angle in the first quadrant, pi over 4, and of course in the second quadrant we have a negative, and then of course cosine of pi over 2 is 0. So we have the additive inverse of the additive inverse, so our answer is 1 over root 2. Now the next one is just, again, remembering I've written this in the blue. We've done this before when we did the antiderivative formula with a conjugate method. So here we have the derivative of cotangent x is the negative cosecant squared of x. So we can work that backwards to get a nice antiderivative formula for the cosecant squared. And so now notice we have to dress this up a little bit. So notice we have the 2x here, so we don't have the 2 dx. So we're going to put in the 2 and then pay for it with the 1/2. And so now we're table ready, so to speak. And so now we go up here and just say, okay, the antiderivative or an antiderivative of cosecant squared 2x will just be the negative 1/2 cotangent 2x. Now let me just make a comment here. You can go ahead and make a u substitution as you could have done up here, but when it's very straightforward like this, there's no reason to do that. And now of course we have an antiderivative, as I've said before. We need to evaluate it at pi over 3 and pi over 4. Now 2 times pi over 3 will give us 2 pi over 3, and 2 times pi over 4 will just give us pi over 2. Now the cotangent of 2 pi over 3 is negative 1 over root 3. Just think cosine over sine. And then of course the cotangent of pi over 2 cosine over sine, that'll give us 0. So we've got negative 1/2 times negative 1 over root 3. The negatives absorb, and we get 1 over 2 root 3. So again, very basic definite integrals, but a very nice utilization of the antiderivative technique with the fundamental theorem of calculus part 2. And we are done.